We will continue where we left in the last class on precipitation. We were talking about one of the solid state phase transformations, precipitation. When you look at precipitation and talk about nucleation of a precipitate, we look at the free energy composition diagram. Let us say we talked about an alpha phase which is nucleating a phase called, let us call it as beta or theta, whatever it is. In a aluminum copper phase diagram we call it as theta, let us say. And if you look at the equilibrium between the two, this is the common tangent which talks about equilibrium, and the corresponding phase diagram is somewhere here, let us say, and this is at whatever temperature it is. Let us say we are talking about room temperature. At room temperature, this particular composition that you are seeing is this composition, right? This we know. So, whatever composition that we are talking about here is this composition. And if you take an alloy of a composition something like this, that is what is the whole edge hardening process that we talk about. So, the alloy is somewhere here, is on the right side of the equilibrium composition of alpha in equilibrium with theta, and that alloy at this temperature, room temperature, this is where we are talking about. At this temperature, if it starts precipitating theta, the driving force for the nucleation of theta is always given by the line which is a tangent for the alloy for the alpha at the alloy composition. At the alloy composition, if I draw a line which is a tangent to alpha free energy curve, and wherever it gets extended at the precipitate phase composition, if you draw a vertical line, this difference indicates the driving force for the nucleation. We call it as delta G for the nucleation. So, anytime you see an alloy, if you want to calculate what is the driving force for nucleation of a particular phase, any phase it could be, in this particular case I am just simply taking an example of theta, and if I am taking theta, simply take that alloy composition. It could be 4% copper, it could be 2% copper, it could be 3% copper, whatever alloy composition it is, and for that alloy composition draw a tangent, and from the tangent position to the free energy of that particular phase at that temperature, what you get is the driving force for the nucleation. And in such a case, if I change my alloy composition, if I choose another alloy composition here, in principle if I draw another tangent here, you would see that that tangent will lead you to a different driving force for the same phase. For the same theta to precipitate out of alpha, alloy 1 and alloy 2 will have different driving force, and the larger the composition of the alloy with respect to the equilibrium composition, the more away the alloy composition with respect to the equilibrium composition, the greater will be the driving force. So, the delta Gn is proportional to delta x naught, we call it, where delta x naught is x minus x naught. What is x naught? X naught is the equilibrium composition. This is very clearly seen here. So, if I choose alloys of different compositions, that is the reason why a 2% copper alloy and a 4% copper alloy will have different driving forces at the same temperature. This I am taking the example of room temperature. I can change the temperature. If I change the temperature also, if I choose some other temperature, there also you would see the same thing. And you can also see it in terms of the phase diagram also. What tells you about the driving force is this. This is the actual driving force, I mean not in terms of delta G for that matter. You are at a temperature, for example if I am considering the same room temperature alloy 1 and alloy 2, for alloy 1 you are at a temperature away from the equilibrium transformation temperature. The moment you are below this equilibrium transformation temperature, there is a driving force for the second phase to precipitate, am I right? If I am at a temperature here, obviously there is no driving force for the second phase to precipitate. If you want second phase to precipitate, I have to come below this temperature, which is what is called the solver's temperature. So the farther away the temperature is from the solver's temperature, the higher the driving force for the precipitation. So for any alloy composition, if I am at different temperatures, so the lower the temperature is, the higher the driving force for that alloy. Now if I am choosing two different compositions and choosing the same temperature, fixing the temperature but changing the alloy composition, you see by changing the alloy composition, what is changing here? Solver's temperature is changing. Whenever I change the alloy composition, for example alloy 2 has a different solver's temperature, this is the solver's temperature here and this is the solver's temperature in this particular case. So because the solver's temperature is changing, is increasing as I increase the solute content, and if I am fixing my transformation temperature where the actual transformation is going on as a fixed temperature, now you see the difference between the solver's temperature to the temperature at which the transformation is taking place is larger in case of alloy 2 and is smaller in case of alloy 1, and that means again you can see that alloy 2 has a greater driving force for the precipitation when compared to alloy 1. So you can see that by choosing an alloy of appropriate composition, and that is the reason why people want to choose as larger solute content as possible, but that is limited by something. You cannot choose any composition of your choice. Limited by what? Limited by it is decided by what is the maximum solubility of the solute in the alloy. That means if I extend this phase diagram somewhere here, I mean let us not bother about what is on the other side, okay, let us only look at this particular composition. This is what decides what is the limit to which I can go. That is the maximum of, if I go beyond this, then what I have a situation where I cannot actually solutionize the alloy. I cannot take it into a single phase solid state, single phase solid solutions condition, because unless I take the alloy to the single phase, there is no, the age hardening does not start. Age hardening process, the first step itself is to take it into a single phase, then quench it, then you try to do aging to precipitate the second phase. So in case you cannot get, for example if I choose an alloy of this composition, this is one of the typical case of a 6% copper alloy, let us say a commercial alloy 2219 alloy. If I take a aluminum 2219 alloy with about 6%, 6.5% of copper, 6.5% of copper, the moment I start heating it, actually in principle as I keep on heating it, what should happen to this alloy? This alloy, this has been solidified, brought to room temperature, now I am heating this in a furnace to different temperatures. What should happen to this alloy? Theta has to dissolve. Why theta has to dissolve? Because the solver's line, if you carefully observe, the solubility of copper in alpha aluminum is increasing with increasing temperature. That is what this line tells you. So because the solubility is increasing, and at each temperature if I calculate what is the volume fraction or the weight fraction of the second phase, the weight fraction of the second phase keeps on decreasing if you use the lever rule, because what is decreasing is this length is decreasing, isn't it? And from that you can feel that from the lever rule the amount of theta is decreasing, and that amount of theta, where should it go? It gets dissolved into the matrix in such a way that the matrix composition gets richer in copper, because the theta which is a copper rich phase is dissolving into the matrix becomes enriched in copper content, and that is what you keep seeing. And until the eutectic temperature, you would see that this will keep on happening, and even at the moment you reach the eutectic temperature, you will still have some theta and some alpha of at the temperature of eutectic. The moment you reach this eutectic temperature, let us say you are just below the eutectic, melting has not yet started. If you are just below the eutectic, then you will see the alpha composition will be this, and you will still have some theta which is decided by this length of the line divided by the total from that to the theta phase, wherever theta phase is, that is how we calculate. So, you can see this tells you that there is still some amount of theta, that means complete solutionizing has not happened, but still you can take such an alloy, and in such an alloy where is the theta? Theta is still at the grain boundaries, though it has dissolved, some amount of theta is still left out at the grain boundaries, because during solidification happens at a slow condition. So, as a result theta is precipitating at the grain boundaries only. So, you will see that the theta is there at the grain boundaries, but the matrix, if you look at it, matrix got enriched, but still you have theta here. And so, this, if from that temperature, let us say if I quench it, what should happen? So, alpha which is there here will remain as supersaturated because I am quenching it, but the theta which is there at the grain boundaries will remain as theta. Depending on what is your alloy composition, some amount of theta will be there according to the phase diagram. And this alpha which is now supersaturated alpha, which has formed at the room temperature when you quenched it, that particular supersaturated alpha is the one which will start precipitating out. So, in such an alloy, you still have edge hardening taking place, you will still have precipitation taking place, but in addition to the precipitates you will also have the theta which has been formed during solidification at the grain boundaries. So, you would still have some theta which is at the grain boundaries, and in fact this theta, how did this theta form? Can somebody tell me during solidification? The theta which you see, it forms from the eutectic reaction. If you look at this alloy and then extrapolate this phase diagram, you have theta somewhere here, let us say, forget about this, if you have, forget about this line. So, this alloy, if I am solidifying it, how does it solidify first? It is a hypoeutectic alloy. So, what comes out first? Alpha dendrites come out first. So, you have the alpha dendrites, and once you reach the eutectic temperature, it is the eutectic mixture which comes out of the liquid. What is the eutectic mixture here? Alpha plus theta. So, at the dendritic boundaries, okay, and these dendrites will get converted into grains later. So, at the grain boundaries where you have actually interdendritic regions, and those regions are the ones where you have the theta. So, theta will be present in the form of not as a precipitated. So, if I look at this alloy will be a different alloy. This alloy will be entirely different from this alloy in terms of what is the morphology of the theta. In this case, you see that this alloy solidifies completely as single phase alpha. Am I right? Solidification is only single phase alpha, there is no eutectic there, and this alpha, as I am cooling to room temperature, it starts precipitating the theta, and that theta comes out at the grain boundaries. Whereas, in this alloy, the theta that comes out, the theta does not come out by precipitation from the alpha, it comes out as a eutectic mixture. But you can still ask me, sir, after the eutectic reaction, when I still cool it from the eutectic temperature to room temperature, what is supposed to happen during solidification? After solidification is completed, but that solid is now cooling to room temperature, should anything happen in that alloy? Should increase. Why it should increase? Because the solubility of copper in alpha is decreasing, and where should that increased theta appear? It cannot nucleate inside. So, in principle it would possibly nucleate on the existing theta which is there during solidification, whatever, because already theta is there in the eutectic mixture, that theta it gets precipitated over that because it does not need further nucleating sites. So, you will usually see the microstructure would look like the dendrites, and in the interdentic regions you will have the whatever may be the morphology. In this particular case actually you see a lamellar morphology. So, you will see actually a lamellae of there can be boundaries which are called eutectic colonies, and you will see lamellae where you have that. And after the solidification, as you further cool, if you want to look at where does this form, so that extra theta phase will start forming on the theta which is already there close to the dendrites, because the excess copper is coming out of the dendrites actually. It is the dendrites which are releasing all the copper. So, as a result nearer to these dendrites you will see the precipitation happens. So, in principle you can also see the theta nucleating either at the grain boundaries, which at the dendrite boundaries, or on the cement on the theta which is already there, okay, one of the two. That is what I am saying, they are alternate layers. The white and the black what you see are the alpha theta. So, that is what you are seeing there. And on this, for example, if copper that is coming out will not go and precipitate on this theta, because it has to travel a farther distance. So, in principle if there is a theta which is already available here, that theta becomes thicker, or the theta will form as a layer on the existing alpha. So, you will have two morphologies of theta, one theta which is already present in the eutectic mixture, and second the theta which is there at the grain boundaries of the dendrite boundaries if you want to call them. Whereas in this case you have the alpha coming out as the grains here after the solidification, and the theta precipitation is only there. And when I am heating this back, now both the thetas start dissolving, one the theta at the dendrite boundaries and the theta which is there within the eutectic mixture, both of them start dissolving, and as a result once you reach this temperature you will have some theta that is left out. And now when you quench it, this particular, because the theta has dissolved, these dendrites now become richer again in copper to the extent of what it would have had just after the eutectic reaction. Just after the eutectic reaction alpha had this composition. So, if you have heated this alloy back to the temperature, you have more or less reached that particular condition where just after the eutectic reaction what was the existing alpha, and that alpha when you quench it, now you will have that alpha retaining all the copper content, and when you start heating it for the edge hardening, that particular alpha precipitates inside it some phase which is depending on whether it is what is undercooling that we are talking about, because in the last class we talked about whether GP zones come out or theta double prime comes out or theta prime comes out or theta comes out, depends on what is the temperature at which we are doing the edge hardening for a given alloy. That is what you have seen, different solvus lines we have drawn, and depending on that we can see that.
But when theta is already there, why it has to nucleate inside the grain?
Because again this copper which is there inside the dendrites, if because we are doing edge hardening at this temperature, let us say, so if it has to nucleate on the theta which is there. So, it has to travel a larger, and these are all 100 microns or so generally grain sizes. So, it has to travel a long distance, and at that temperature it is not easy for it to happen, and that is the reason why it avoids, because the time available is shorter, and otherwise in principle if you leave it forever you will see slowly the diffusion can happen, and then some precipitation can happen at the grain boundaries also. But otherwise, because the time available is shorter and the temperature is very small and the diffusion is difficult, and at the same time the alpha is supersaturated and it is not stable, because we can see here it is not stable, alpha, single phase alpha is not stable, it wants to precipitate, it has a higher free energy than a two phase mixture, and as a result it wants to come out as bring out the precipitate, and that can happen only by precipitating within the grain. So, this is how you will see if you have a composition of that sort. But if you are talking of compositions which are to the left of it, and most of the precipitation hardening we are only talking about those compositions, we are actually not talking about this kind of composition, because this kind of compositions are not ideally suited for edge hardening, because you will somehow have some prior theta which has been formed during solidification, and as a result the full advantage of edge hardening, which is a combination of ductility and strength that you want to have, is not possible to be achieved because of this kind of samples, and as a result you always try to restrict to let us say 4%, 4.5%, 5%. In fact, though I say this is the limit, in principle you do not even reach there, because there is another problem that is associated with it. What is the problem? For example, if I choose this alloy, you may say, sir, this alloy is still to the left of the maximum solubility, why can't I use that alloy?
The range between solvus and
Yes, the range between the solvus and solidus is very small. When that is very small, when you want to do homogenization treatment, what we call in steels as austenization treatment, so here we call it as a homogenization treatment. So, during that homogenization, if you do not maintain your furnace temperature carefully, you end up into this domain. Once you end up into that domain, some liquid forms, and the liquid usually forms at the grain boundaries. So, which the moment liquid forms, immediately you will see the liquid composition will be something of this sort, and that liquid when you start quenching it, it starts precipitating out some theta at that grain boundaries. So, you cannot prevent that liquid to solidify. So, that is the reason why we do not want to go into a liquid state, because you are not in a single phase state, you are into a two phase region, and the whole purpose of solutionizing or whole purpose of homogenizing is to get into a single phase state, you do not want to come to a two phase state. So, that is the reason why you have to have a reasonable margin, considering the furnaces that are used in the industries where the temperature ranges, I mean accuracies would not be of the order of 1 degree or so, they could be of the order of 10 degree or 20 degree. So, you need to consider that so as to define what is the maximum composition to which I can go. So, the reason why I am saying all this is, the higher the composition, the higher the driving force, and for the same alloy composition the driving force can be further changed by simply changing what? Temperature. Okay. So, once I fix up my composition, the only way I can change the driving force is by changing the temperature. So, a higher temperature or a lower temperature, which is preferable? A lower temperature will have a higher driving force. So, that means you can say that the delta x naught is proportional to delta T. Alright. So, the higher the undercooling, so instead of choosing a temperature of this sort, if I choose a temperature of this, so obviously you see here this is the delta T, and in this case this is the delta T. The higher the delta T, the higher the driving force. The driving force, you can see the extent of supersaturation is larger, and here the extent of supersaturation is smaller. And you can also see on the free energy diagram, how does the free energy diagram change with respect to this temperature and this temperature? which will shift up, which will shift down. Let us say for example, instead of temperature 1 I have increased to temperature 2, what would happen to the free energy curves? Both will go up, and then relative movement of theta will be larger, okay, and then how does it shift the delta G? We are all bothered about that. How does the delta G change? Will the delta G change? Delta G, I mean for the moment I fix up my alloy composition, this is my alloy composition, this is the delta G that I am talking about, this is the overall driving force, and whereas this is the, let us say I am talking of this alloy. So, this is the delta G for nucleation. We have two delta G's, one is the overall driving force for the precipitation, this is the driving force for the nucleation, just for the nucleus to form at the start of nucleation, but this is for the complete transformation, what is the delta G, and this delta G how will it change by changing the temperature? It will decrease. Why will it decrease?
Theta goes faster.
Common tangent is shifting.
Yes. So, the moment you see that this goes up with respect to alpha, what should happen? So, for example, let us say assume that this theta has shifted to this to this. Now, alloy composition is fixed, your alloy has not changed, what has changed is this common tangent composition. That means the composition of alpha in equilibrium with theta has shifted, and that is shifted to a higher copper content. Once that is shifted to a higher copper content, this value decreases, and that is how you can say. So, the higher the temperature, the lower the stability of theta, because theta is dissolving at high temperature, theta is not stable. So, as a result theta grows faster, okay, theta free energy rises faster, and once that happens with respect to alpha, you would see the common tangents change, and that is how we can say the driving force changes. So, the driving force can be easily seen as a function of both composition of the alloy and the temperature, both of them decide this, and at the same time we also know that this driving force, there is something which has to be considered, which is something which is a strain energy, which is also a volume free energy, which has to be deducted whenever you talk about the total driving force. In case of a liquid to solid transformation, we never considered this. So, here in case of solid solid transformation, we have already said that whenever I say I have this much of driving force, the realistic driving force that is available is this minus this, and that has to be sufficiently enough to take care of your surface energy term. Surface energy term is in terms of the per unit area, whereas this two are per unit volume. So, that is why if you look at, for example, a case like you remember this is the gamma term, this is delta G V term. The moment you consider this term will be higher, this is actually negative, and the extent of negative decreases because this is a positive term, and as a result the activation barrier that you are going to get is going to be higher activation barrier. So, the moment I consider a strain energy term in a solid state transformation, so this activation barrier, which is the delta G star that you get, if you again calculate using the delta G, which is a summation of the overall energies plus gamma, A gamma and V, and the way we do is put this values V and A in terms of the R, and then differentiate free energy with respect to R, and then equate that differential to 0, and that is how you get these values, is not it, R star and delta G star. And if you try to look at this delta G star, the delta G star value is going to be larger here because this delta G has got decreased. So in principle, if you write R star expression, you remember this, you get this delta G 2 gamma minus 2 gamma by delta G. Here you have to consider this. So wherever delta G is there, you will see that delta G becomes delta G minus delta G epsilon, because both are volume terms. So as a result, the R star is going to be larger because this is decreased. So you will have a bigger nucleus, and then if you again put this back into the delta G star term and calculate the delta G star again 16 pi by 3 gamma cube by delta GV square. So you will see delta GV minus delta G epsilon square. Again, because this value is decreased, this value will be higher. So you will see the moment we talk about solid state transformations, you need to consider that these things, the strain energy particularly, which is a new term that is coming up, and that new term will decrease everything. And because of that, in principle, if you even consider if I take an alloy of this composition, this is the actual transformation temperature for that particular composition, which is what we call it as Solver's line. This is assuming there is no strain energy term. All phase diagrams when we draw, we do not consider any strain energy term, we do not even consider surface energy term also. So in principle, now the moment you consider the strain energy term, you will see the transformation temperature comes down. Transformation does not happen there, it happens at a lower temperature, because only when you come to a lower temperature you have sufficient driving force which can overcome the strain energy term, so that you have the actual transformation taking place. So if you now consider the Solver's line considering the strain energy, you would see a new Solver's line coming up. This has nothing to do with the theta double prime solvers or theta prime solvers that we have talked about it. Simply just whatever may be the phase that is coming out, as long as this is a non-zero term. When will this be non-zero? When will this be a 0? When you have a perfect coherency, when the misfit is 0. Whenever the misfit is 0, and misfit being 0 is a too idealistic a situation. So when the misfit is 0, in principle this is 0, and when that is 0, then everything changes, this becomes equal to this, and these values will be similar to a liquid to solid transformation, we need not have to bother about it, and then this Solver's line gets shifted to that. So you can see that all these things are shifted just because of one term called the strain energy term, which comes in, and that is why all the solid state transformations are somehow trying to see how do we minimize the strain energy and the surface energy. This is what we have talked in the last class also, where the system tries to minimize the strain energy by choosing that particular phase which can be coherent, so that the surface energy is minimum, and at the same time that particular shape which can have the minimum strain energy. This is how we have seen. Now let us look at
when theta is precipitating as a eutectic mixture, coming out as eutectic mixture, can we say that theta is precipitating at the grain boundaries when theta is alpha also?
There is no precipitation. Where is the grain there? When you still have a liquid there, what do you talk about grain? Let us say, how is the solidification? This is all the liquid, okay, and then inside the liquid you have the alpha dendrites which have come out, these are all the dendrites. Of course you can have side branches and things like that. So now the liquid that is left out is somewhere between these regions, this is all the liquid. There is no grain boundary still here. We can only talk of regions which are interdendritic regions between the dendrites, and the liquid that is left out between the dendrites is the one which is undergoing the thing. Then the question is, where does this eutectic nucleate? And in fact another question also people always bothered for quite some time is, what nucleates in the eutectic? If you have an alpha plus theta in a typical eutectic phase diagram, this was and in the eutectoid, lot of people studied eutectoid in much more detail because it is a solid, you can easily study because you can have an XRD going to that temperature, and also you can quench that after just the precipitation has started, reaction has started, eutectic reaction, you can quench it and then see what is the phase that is coming out. But from a liquid to solid, it is not easy to find out what is actually the first one to nucleate in a eutectic mixture, because whenever you say there are two phases which are nucleating simultaneously, how do they nucleate simultaneously? Because both of them have two different structures, one is alpha, another is theta in this particular case. Let us say, how do alpha which is an FCC structure, theta which is an orthorhombic structure nucleate simultaneously? It is not a easy thing. That is where people have seen that if it is a hypoeutectic or a hypereutectic, life is very easy, because if it is a hypoeutectic you already have an alpha dendrites. So in the eutectic mixture, when the eutectic mixture is forming, you can have the nucleation that can occur on the alpha which is already there, and because it is alpha that is already there, it will be the alpha of the eutectic mixture which will nucleate first. And the moment alpha forms, because alpha is a pure aluminum kind of a composition, the regions which are next to it become rich in copper, so theta comes out. So it is like one follows the other, the theta follows the alpha. So that is how, though nobody has actually seen the nucleation, it is not easy to see what, because that happens in such a fraction of a second and in such a small scale, a few nanometer scale. So you really need very high resolution microscopes to be able to catch that nucleation event, and also catch in situ. If you can keep a liquid at that temperature in a high resolution electron microscope, let us say, and then cool it and then see the solidification happening, you can really see it at a high resolution state, but it is not so easy. So that is easy to understand on a hypo. On the hyper we already know it is the theta that has already come out. So you can say the theta of the eutectic mixture nucleates on the theta which is already existing. But if you are exactly the eutectic composition, it is very difficult to say. That is where people say the phase which is easier to nucleate, which has a lower activation barrier, whose structure is similar to that of the liquid structure, is what nucleates first. So that is where people always say FCC kind of phases are more easy to nucleate than orthorhombic kind of phases, and that too it is an intermetallic compound. So intermetallic compound nucleation is more difficult than a solid solution nucleating, because solid solution it is all random, chemically it is random, structurally not random, but chemically it is random. Whereas intermetallic compound you have an ordered structure, so you have fixed positions for the copper and aluminum sitting there. So that is why it is more difficult to nucleate. Anyway, those are the issues. So here there is no grain boundary that we talk about. So the nucleation starts, let us say, here. So if I enlarge it, let us say this is the thing, so you will have things like that. So the moment a small nucleus of, let us say, alpha nucleates, next to it becomes the theta, and both sides the theta. Once the theta comes, the region next to it again becomes poorer in copper, so alpha comes out. So that is how a small colony forms, and that colony starts growing, and there will be another colony somewhere else, another nucleation event. So you see the whole nucleation is actually on the alpha and then grows into the liquid. This is how it happens.
So but when I melt it, I got atoms of copper and aluminum
inside the liquid, aluminum and alpha.
Does the short range order of aluminum and copper
See, this is the interesting thing. When you say short range order, okay, so inside the liquid when aluminum and copper are there, it is not that all aluminum copper atoms are segregated somewhere, all copper atoms are segregated somewhere else. It is all a mixture. It is a liquid solution where inside the liquid copper atoms are statistically there, whatever is the percentage. So, the probability of finding a copper atom at any particular point will be, let us say 0.04, because 4% of copper, let us say. So, that is how you should look at it.
But when I cool it, how does the copper atoms assume the orthorhombic structure?
Yeah, because there are, you see, the question is the phase is stable. So, the moment alpha comes out, the remaining copper atoms that are there, because the phase that is most stable there has the lowest free energy is the orthorhombic, no other structure has a lower free energy, the atoms get rearranged themselves to that particular structure.
Why copper cannot become FCC?
Because it is not stable, as simple as that, it is not stable. According to the phase diagram, if you look at it, for that alloy composition, this is the stable, you cannot get anything else. The question is why, for example, aluminum, why FCC, why not BCC? The same argument holds good here. Though copper atoms are there, the copper atoms could, sometimes you can get what are called metastable phases. For example, you have seen, we have seen a number of cases where when you are cooling, even in precipitation hardening also we are seeing the GP zones, theta double prime, theta prime, these are all metastable phases, they are not the stable phases. The ultimate stable phase is the theta phase, am I right? Similarly, during liquid to solid transformation also, sometimes you may get, particularly when you are cooling it rapidly. For example, assume that this alloy is being cooled very rapidly, then the theta phase, which is orthorhombic, you said it is more difficult to nucleate, so it is very difficult for it to nucleate. So, the system will try to choose that particular phase which can easily nucleate if there is a metastable phase, but that would be remain always as a metastable phase, provided you heat it, it will come back to the theta phase. There are quasicrystalline phases also which form generally when you cool it, quench it, many alloys people have seen, particularly aluminum alloys, aluminum iron, aluminum vanadium, aluminum manganese, a number of cases people have seen quasicrystals form when you take the liquid and quench it, because the quasicrystalline structure, the clusters, the short range order inside the liquid is similar to that of the arrangement in the quasicrystalline structure. So, as a result you will see the liquid prefers to give you this rather than the equilibrium intermetallic compounds, but these phases are metastable. Obviously, when you heat the quasicrystal, it gives back the equilibrium phase.
How is a quasicrystal different from a amorphous structure? Because we are quenching a liquid, there will be a certain amount of charging that will be within the amorphous structure.
Yes, correct. The difference between the two is it has a structure. A quasicrystal, as the name suggests, it is a crystal. It is one type of a crystal. The only thing that is missing in a quasicrystal is what is the translation periodicity. I do not know how many of you read about crystal. Any crystal, I mean we are deviating, but maybe we will talk at some other time. Any crystal has two types of symmetries. One is called rotational symmetry, another is called translational symmetry. Have you heard of this? A translation symmetry means if you take an atom here and go in a particular direction by a particular unit distance x, let us say, you find another atom, and in the same direction move by another x, you should find the third atom. The moment you find it, you say yes, there is a translation symmetry. That is what we call it as periodicity. And what is this rotational symmetry? That means around a particular atom, if I rotate the unit cell in a particular angle, that unit cell you would see would merge into itself, no new spots are generated. For example, if you take a cube and I rotate along an axis which is a z axis, let us say, by a 90 degrees, you will see this that unit cell, the new positions that you are creating, you are not going to differentiate from the old positions. Take any square, rotate around this, you will see this spot goes here, this spot goes here, this spot goes here, 90 degrees, and that is what we talk about rotational symmetry. A quasicrystal has rotational symmetry but does not have translation symmetry. A crystal has both, an amorphous does not have both. So it only has a short range order, it does not have a long range order, but a quasicrystal has a long range order. Long range crystalline order in terms of its rotational symmetry, only thing is it has special rotational symmetries. What are those special? For example, a normal crystal has a 2-fold, a 3-fold, a 4-fold and a 6-fold. You cannot have any other symmetry other than these. Of course, you can also have a 1-fold symmetry, which is what we call it as a trivial symmetry in a crystallography. So these are the possible symmetries, everything else is called forbidden symmetry. For example, a 5-fold symmetry cannot exist in a crystal. Any of you want to know why? You should go to solid state physics by Kittel, he tries to prove it. I can also prove it in a minute, and basically that such a rotational symmetry, a 5-fold symmetry, does not guarantee a translational symmetry. That is the problem. The moment you have a 5-fold symmetry, you cannot have a translation symmetry, whereas all these symmetries you can simultaneously have a translation symmetry. You can just go back to any crystallography book and try to see the proof of it. So that is the reason why a 5-fold, 7-fold, 8-fold, any other thing other than these are all forbidden. For the first time in 1984, a person by name Shetman saw in an alloy of aluminum 14% manganese. When he prepared this alloy by fast cooling, the technique that Paul Dewey used, rapid solidification, and took that the foil that came out of it and put it into a TEM, and he observed a diffraction pattern which has a 5-fold symmetry. That was the first time anybody has actually seen a 5-fold symmetry in a diffraction pattern. So the diffraction pattern looked like this, a spot, central spot with some 10 spots around it at equidistant, 3 plus 3, okay, whatever it is, equidistant. So 10 spots on a circular ring, let us say, which actually looks like a 10-fold, and if you know a little more crystallography, you can know how to differentiate between a 10-fold and a 5-fold. There is something called Friedel's law. If you read electron microscopy, you will come across that. So where we can differentiate between how to see a 5-fold and a 10-fold, but basically even if it is considered as a 10-fold, 10-fold is not possible under normal conditions. So the moment he saw that, then he tried to repeat it a number of times, and every time he got the same thing. That is when people started accepting, yes, possibly this can exist, and that is when they said these we cannot call them as crystals, so let us call them as quasicrystals. The only difference between this alloy and an amorphous alloy, when you do an X-ray diffraction, an amorphous alloy, what do you see in an X-ray diffraction? You see a broad peak, whereas this quasicrystal you see sharp peaks, exactly the same way as a crystal. So you get sharp peaks. In fact, that is where recently around end of 90s or so, people, till then the definition of a crystal is that which has both rotational and translational symmetries, they used to define. Now they say a crystal is that which shows a sharp diffraction pattern. So after people have discovered quasicrystals, people had to change their definition of a crystal. We always used to, if you ever remember in the second year BTech, when you start knowing crystal structures, you said crystal is that which has a periodicity, isn't it? Something which is periodic is what is a crystal. This is not periodic, but this is also one type of a crystal. So people had to really change the definition, and the crystallographers had to accept that there are alloys like this, materials like this, which can give you rotational symmetries which are forbidden under normal conditions. But if you try to, it is simple. You imagine if I have to show you in a 2D a pentagon, if I keep on putting pentagons next to each other, you will always have some gaps left out, and that is what is the difference. If you take square, you can keep on joining squares. You take rectangles, you can do that. You can take a equilateral triangle, you can keep on joining. This is what we call them as tiles. For example, you can see a square tiles there. You cannot have pentagonal tiles and still have no gaps left out. That is where the problem comes. So, if you take such a quasicrystalline unit cell and keep joining them, you will always have some voids left out, which we call it as a frustration in crystallography. So, you will always have such voids left out, and that is why people say these alloys have, these phases have a high energy state, they are at a high energy state because of those voids that are available, they are at a higher energy state, and that is why they are more metastable when compared to the stable structures. Okay, we will stop now.